So I will begin with the verse for the day. According to my son, my 7-year-old, the verse for today is Genesis 1:1, which is simple enough to remember. In the beginning, God created the heavens and the earth. I think it's a good place to start, and I think it's actually pretty relevant to physics. But anyway, I'll begin with a word of prayer then. Dear Heavenly Father, we thank you for this day again. I thank you for this class, these students. Just ask that you bless our work today. Help us to glorify you what we do and just to understand a little bit more about vectors, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me get straight into it. So if we have a vector in the plane, we can talk about its standard angle. So here's x, here's y. This is my vector, A, right? Then the standard angle is the counterclockwise angle swept from the positive x-axis. We typically use theta for the standard angle, but beware, we use theta for more general angles. Theta doesn't have to be the standard angle. This notation does not necessarily make it the standard angle. All right, so, but as I've drawn it is the standard angle. Now, of course, we can look at the x and the y components. Here they are, right? And this would be a sub x. And the magnitude we call a. So a sub x is equal to a cos theta. And a sub y would be equal to a sine theta by trigonometry, right? The neat thing about those formulas is they continue to be true in the other quadrants, quadrants 2, 3, and 4, where sine and cosine are appropriately assigned plus or minus as to reflect the nature of the sine of x or y in those other quadrants. So yeah, that's pretty much it. These equations tell you something. For instance, if we look at a sub y over a sub x, we get a sine theta over a cosine theta, and that gives me tangent theta, right? So there's something that's true. Tangent theta is equal to a sub y over a sub x. Now, that's helpful, but it can also be misleading, all right? It is not always the case that theta is the inverse tangent of a sub y over a sub x, all right? Let's look at some examples of that. So example 1. Well, I'll start out with a positive example. Here's a pretty simple one. Let's look at the vector 2, 2. So plotting that, something like this. Here's your theta, right? This distance is 2. This distance is 2, right? So this makes tangent theta equals to 2 over 2, also known as 1. And theta we can calculate from inverse tangent of 1, which is 45 degrees. So the standard angle here is 45 degrees. All right? But, as I said, a little foreshadowing, this doesn't always work. You have to think about it, generally speaking. So example 2, if I had, say, this vector, say minus 10, minus 10, all right? Like that. All right? So what's the standard angle? Well, if I picture it, it looks like this, right? So, there's some benchmarks to remember is like the positive y-axis is 90 degrees. Let me write those out here. So you got 90 degrees up here. You've got 180 degrees over here. This guy is 270. And of course, you start at 0 degrees. Now, you can also go minus, right? Like 270 is the same as minus 90 degrees. We always have this ability to shift by 360 degrees because sine and cosine are 360 degree periodic. So I might ask for the standard angle, and some of you might give me minus 90 degrees, and others would give you might give me 270 degrees for a problem. And I'd be like, yay, you're both right, all right? So they both get credit. Now here, tangent theta, right, is equal to, well, minus 10 over minus 10, which is still what? 1. So if I was to calculate inverse tangent, what do I get? I get 45 degrees. Is that correct? It's not, right? Inverse tangent is only a legitimate tool. So like, so the range of inverse tangent is equal to basically minus 90 degrees, comma 90 degrees. You can try it out on your calculator. It will always give you back plus to minus 90 degrees. So inverse tangent of this equation does not give us the truth, because inverse tangent is what's called a local inverse, right? So how do you figure it out? So you just, use common sense here. Basically, theta is equal to, let's see here, 180 degrees plus 45 degrees. See, because this angle is clearly 45, right? So I go 180 and then another 45. So the standard angle in this case is 225 degrees. All right. So you're like, I can't just use inverse tangent of the y over the x. Correct. You cannot do that. You have to think through it. Your angle, standard angle, should be appropriate to where the vector is, right? If the vector is in quadrant 2, it better have an angle between 90 degrees and 180. If it's in quadrant 3, it should be between 180 and 270, right? But inverse tangent will serve you well if you're where x is positive, all right? Okay, got that out of my system. So there's the standard angle. So if you're a little bit more here, what's the connection between the standard angle and the unit vector? So direction. Is there one direction? Well, no. There's two directions, two ways. All right, so if we have a vector A and it's not equal to 0, on the one hand, we can write it as a sub x, a sub y. That's just like the basic terminology, all right? And so one thing you can do is rewrite this in terms of the magnitude times the cosine of the standard angle, the magnitude times the sine of the standard angle. Now you remember, a without the vector is the length of a, right? A without the vector is the square root of ax squared plus ay squared, okay? Now, then what? Well, I've got a common thing of a here, right? So I can pull out a, and I've got cosine theta, sine theta. All right? On the other hand, remember last time we defined the unit vector? We said that a hat was what? It's 1 over the magnitude of a times the a vector, right? Or, as I like to remember it sometimes, any vector can be written as a product of its magnitude and direction. So this gives us that a vector is equal to the magnitude times a hat, right? So I have two different ways I can think of the direction of a two-dimensional vector. I can either think of it in terms of a unit vector, right? Or I can think of it in terms of the standard angle. And the connection between those two, you can see right from here in this, right? What does this tell us? This tells us that a hat can also be written as what? Cosine theta, sine theta, right? So this is the connection between the unit vector and the standard angle. Any questions? All right. Let us go on then. Example 3. Suppose we have A, which is 40 degrees north of west. We have B, which is 30 degrees east of south. And then C, which is at the standard angle theta equal to, I don't know what you guys want, 130 degrees. All right? So let me draw a picture of what's going on here. So we're given these three vectors, and the question is to find the magnitude and standard angle for D, which is formed by A plus B plus C. All right, that's the question. And I'm also going to give us the magnitudes of A, B, and C once I draw the picture, okay? I haven't done that yet. So I'm going to add a little bit more up there. I'm going to add the magnitudes in just a sec, okay? So here's a picture. All right, so first of all, A is 40 degrees north of west. What's that mean? That means you go in the western direction. So we take X to be east, we take Y to be north. That's how we go in here. And 40 degrees north of west means you point in the western direction like that, and you sweep towards the north. All right, so 40 degrees north of west is something like this, right? So that makes this angle right here 40 degrees. All right, is that a standard angle? It is not, all right? Next up, let's picture B, 30 degrees east of south. What would that mean? So we go this way, excuse me, south, right? East of south. All right, so this is south, and we go 30 degrees east of that. So that means we sweep this way. So there would be your B vector. And this angle here would be 30 degrees, as I've worded it. 30 degrees east of the south, all right? And then finally, 130 degrees, C is at 130 degrees. Let me do that in, I'll use purple. So if you think about that, that's 90 degrees plus 40 degrees, right? So you're sweeping 40 degrees off the positive y-axis. It's something like, kind of sort of like this. All right, so there's your B. Okay? Now the magnitudes, I'll figure out now. Let's see here. Magnitude of A is going to be 13. The magnitude of B is going to be 12. Let me write that down before I forget it. A equals to 13. B equals to 12. Oh, wait a minute. Oopsie. This one was 12, wasn't it? Look what I did. You guys see what I did? Is this B? No. What was it? C. Dummy. Me, not you. Let's see here. So this was, the blue one was A, right? Oh, my goodness. If you missed what just happened, you didn't miss much, all right? So the point is that this angle here is 130 degrees. All right. So A was 13, C was 12, B I haven't measured yet. B is in fact 10. So, all right. So the magnitude of B is 10. And of course, we could be working now, like, you could think of these as force vectors. All right, so we would be calculating the net force by the sum of the forces acting on the point, for example. We could think of it that way. You could think of these as like successive displacements of a mouse or something. So the sum of the displacements would give you the total displacement from the motion. If you wanted to think of it that way, probably what you'd want to do is look at all three of these vectors, like tip to tail, one after the other. All right. But anyway, so we're supposed to add these together. Now, how do you do a problem like this? The way to do it is to break each vector into its so-called Cartesian components. All right. So first of all, C is easiest, right? C is equal to 12 times the cosine of 130, and then the sine of 130. All right. So C is equal to, what we got here? Hope I'm in degree mode. I'll tell you what, if you're in radian mode and you think you're in degree mode, that's a bad day on the test, isn't it? Let's see here. Something to think about. Minus 7.71. I mean, I will give you partial credit, but nevertheless, it would be nice. It'd be nice to get all the credit, right? Let's see here. 12 times sine of 130. 9.1925. I'll keep a fifth digit there. I usually try to keep 5 digits in the calculations and then keep 4 in the answer. So it's actually 7.7135 if I round up. There. All right. So there's C. How about B? What's B? So B, let me take a different tact here in my work for B. Let's just kind of look at it. If you look here, right, you can see that we've got what? We've got a right triangle, right? The hypotenuse is 10. The angle here is 30 degrees. So to get the opposite, I do sine times the hypotenuse, which sine of 30 is 1/2, so this is going to be 5. And then over here, I would get, so in other words, b sub x is equal to 10 times the sine of 30 in this context, which is equal to 5. And b sub y is 10 times the cosine of 30. And you guys tell me why that's wrong. Well, that's part of it. You're like, wait a minute, you used cosine for the y, but I thought cosine goes with the x. You're right, it's not a standard angle, so that's out the window. Yep.
It's because it's in the fourth quadrant. Be careful about the signs.
Yeah, be careful about the signs, the SIGNs. Y is pointing down, it should have a negative y component for B, right? So exactly that. So I'm missing A. Minus. The minus has to be put in by logic, right? Which you guys know, right? Like thinking. You guys can think. I know it. Don't try to tell me you can't think. I know you can think. So my calculator annoyingly gives me 5√3, which is a lovely answer for a calculus class, but a worthless answer for us here. And I will hit the S. There's a you can switch from the exact to the decimal here. So we get minus 8.6603, let's say. All right, there's my B. So I've got C, I've got B, and now I need to figure out A. And listen, like, yeah, you can always go back to standard angles and just mindlessly use the standard angle formulas. That's fine. I personally, though, prefer to think about little reference triangles and just add the signs in SIGNs by hand. That's how I typically operate when I think through these things. So let's see here. Break it down. This one here, right? We've got, what was the magnitude of A was 13. So we should have A sub x is minus 13 cosine 40, because that's the adjacent side to that angle. And A sub y should be 13 sine of 40. All right? And so you guys want to tell me what those are? Or not?
X is 9.9586 rounded.
Okay. And A sub y is what? I got 8.3562. All right. Okay, so at this point, we broke down all the vectors into their Cartesian components. Why do you want to do that? Because now we can add the vectors. All right. And let's be neat about it. I like to make a table. All right. So here's my x, here's my y, here's my vectors, A, B, C, and then down here D, which is A plus B plus C. All right. And let's just gather together all of the information that we have calculated, right? So like my A was 8.3562. My x component for B was 5. My x component for C was minus 7.7135. My x component for A was, oh, my bad, y component. I'm to the y's now. Wait a minute. Hold on a second. What did I do? You guys tell me what I did. So this is one of those points in lecture where you do better to like do it yourself and then look up at the board once you're done to see if your table matches mine, right? Like, is it best to mindlessly just copy what the professor puts on the board when you're taking notes? Probably not, right? If you work it out for yourself as you go, you're going to get more out of the class. So like here, you maybe already realized I made a typo there, right? Because that was supposed to be the x component for A, which is what? Minus 9.9586. I learned that from Sprano. Let's see here, 86. Little handy racing action right there. Let's see here. Where was I? B sub y is minus 8.6603. And what's C sub y? C sub y 9.1925. And how do you add vectors? Algebraically, you just add their components, right? So all I got to do now is add those numbers up, and that will give me the x component of D and the y component of D. So let's do it. So 5 minus 9.9586 minus 7.7135. I got a minus 12.672. And let's see here. If you get something else, let me know, okay? Oops. Where's that delete button? Where's my delete button? Oh, there it is. Where was I? Oh, 6. I get, that's funny. I couldn't have planned that if I wanted to. Check that out. Okay, there's a 4, but yeah. All right. So now we have found the Cartesian form of the resultant, right? This is the Cartesian form of the resultant. You guys tell me what's the magnitude here? D is the square root of, minus 12.672 squared plus 8.8884 squared. What's that give me? And do you really care about the minus? It gets eaten by the, I'm just saying logically it's there, but in practice it doesn't matter.
15.48.
Yeah, 15.48 if we're going to keep 4 exactly. So there's the magnitude of the resultant, 15.48. And what's the so let's draw a picture of it. What's it look like? Right? Let me see if I can kind of, so it's in the negative x direction and it's up a little bit. If I was to try to recapture the magic here, A does something like this, right? And then if we draw B tip to tail, then B goes down like this, right? And then what does C do? C goes up like that. So poor I put the B label exactly in the wrong place, right? Oh well. So that's what's going on. If you think about it if you think of these vectors as displacements of, say a mouse or a ninja, an evil cat, that's the only kind there are, whatever you want, then this would be the net displacement. Doo-dook, doo-dook, doo-dook. And so this D vector, if I was to plot it, and then it's going to get kind of messy when I do, right? Because D is this guy, right? There's my D vector. And the standard angle we should expect is somewhere between 90 degrees and and listen, so I've already used theta before, right? So if you're worried about degeneracy, you could put a little sub d on here and say, hey, it's the standard angle for D, all right? But I do tend to use theta as sort of like a garbage variable that I just kind of, I keep reusing it like you guys do in the programming. Okay, so then what? Operator overloading aside. How do you figure out the standard angle here? What should I do? Here's what I would do. I would just say, okay, so theta sub d is equal to 180 degrees minus the inverse tangent of apparently 8.8884 divided by 12.672. Notice I am ignoring the sign, and I'm just thinking about the little reference triangle that the vector D makes with the negative x-axis, right? That inverse tangent gives me the angle it takes to sweep right here, right? This angle, let me call it beta for a second. So this is beta in terms of right triangle trigonometry, and then we can work that out. All right, what is that going to give us? 180 minus the inverse tangent of 8.884. Oh, I lost an 8. Divided by 672. I get 144.95. I guess I'll call it 145 degrees. All right. Any questions? Yeah.
So how come we don't use the negative sign? We omit the negative sign for the x value for when calculating theta d subscript d again?
I'm just using trigonometry. What I'm saying is that the total angle is 180 degrees, but I'm less this acute angle here. To find that acute angle, I simply think about the right triangle that has side lengths, vertical length 8.84 here and 12.672 there. So it's just trigonometry. Yeah.
If we wanted to keep the minus 12 part, would we do 90 degrees plus the inverse?
Oh, I'm not going to say you. I'm not saying you're wrong. I'm saying I'm not going to say there's like a dozen other ways to do it. This is the way I did it. So like, there is like a stone cold formula for calculating the standard angle from a given vector. But if you look it up on Wikipedia, it's got like 5 different cases. It's a case-wise defined formula, inverse tangent in quadrants 1 and 2. If you're on the negative y-axis, that's minus 90 degrees. If you're on the positive y-axis, it's 90 degrees. Those things have division by 0 for y over x, so you can't do that. And then you either have to add or subtract 180 depending on what you're doing for the other 2 quadrants. So it's complicated, and I think about it in terms of right triangle trigonometry personally. So that's what I'm advocating. I'm also more importantly, draw a picture, check yourself, right? So, yeah. Okay. So let's get 3D. Enough of this 2D stuff, right? The time has come to get 3-dimensional. How's this? So in 3 dimensions, have I talked about 3 dimensions yet? I mean, we calculated the distance from the foot to the head, right? That was 3-dimensional. And then I kind of jumped back here into a 2D world. But we need to get back into 3-dimensional world, and we need to talk about, direction of vectors in the 3-dimensional context. So in 3 dimensions, we don't have the luxury of just describing the vector by a single angle, right? There's just not enough information. So let's see here. I'm what example am I on? Example 4. Let's see here. If I had A equal to, let's say, 1, 2, 3. All right. Let me just try to explain for a second here how I visualize that. So I can write this as x hat plus 2y hat plus 3z hat, right? And the way that works is I go 1x hat over, right? And then I go 2y hats this way, right? And then I go 3 z hats like so. Now these these are vectors of length 1, all right? So in this context, the way I draw this picture, and this is the usual thing from like Calc 3 or whatever, there's other ways you could label the axes. This is just my default XYZ three-dimensional perspective picture. So the vector A here is where? I'm basing it at the origin, right? And it's this vector right here, right? In my picture, it would be this. What's the length of A? So the magnitude, this is another notation. This means length of A is equal to A. It's the square root of 1 squared plus 2 squared plus 3 squared. That's also the distance from the base of the vector, which I put at the origin, to the tip of the vector, which actually goes to the point 1, 2, 3. All right? So just a kind of notational, like, wait a minute, what's the difference between the you know, parentheses 1, 2, 3 versus the angle brackets 1, 2, 3? The difference is this: when I write angle brackets, I'm thinking of a vector, which is a directed line segment. When I write just parentheses, I'm thinking of a point, which is a mathematical idealization. It's a single point in space. All right? You can always identify any point with the vector which points to that point from the origin. So you can kind of interchange these two things in context. What's this? This is the square root of, what we got? 14? What does that work out to? Well, if you'll forgive me, I'll not decimal. I won't belabor the decimals here. Oh, I've already walked over here. 3.742. Anyway, you could do that. All right, 3.742-ish. Now, what's the unit vector here? A hat would be 1 over A times A, right? Which is 1 over 3.742-ish times 1, 2, 3. Specifically, that gives us the following. If I keep it, I'm keeping a few more digits in my calculator. So this is 0.2673. Multiply that by 2. I get 0.5345. And then I'm dividing that by 2 and multiplying it by 3. That gives me 0.08. See, my bad. 0.8018. There you go. So that is the unit vector in the direction of A. Okay? That's the unit vector in the direction of A. All right. If you suppose you want a vector of length, let's say 13, that points in the same direction as A, well, how would you get it? What would that be? What is a vector of length 13 that points in the same direction as A? The answer to the question I just posed is simply 13 A hat is a vector length 13 in a direction. So that's like one use of the unit vector. Anyway, we're going to talk more about it, so let's go on here. So at this point, it's time for me to introduce for you the dot product. The dot product, or the scalar product, is extremely important, and it helps us sort of fill in the gap in terms of geometry of 3 dimensions. It gives us a way of measuring angles between two vectors. Let me explain to you how. So the definition is that A dot B is equal to AX BX plus AY BY plus AZ BZ. All right, that's the definition of the dot product. It takes two vectors in, and it gives you a number that comes out. All right. You can prove, and this is essentially the law of cosines. But the law of cosines will allow you to prove that this is in fact equal to AB times the cosine of the angle between them, which I usually use theta for, but you should keep in mind that that is not the standard angle. That's just the angle between A and B. If this is a danger for you, instead of using theta, write alpha there. I don't care. You want me to write alpha? I'll write alpha. Here, for you guys, I'm going to put an alpha here. It doesn't really matter what you call it. The point is, here's your vector A, here's your vector B. The angle I'm talking about is this one right here. Okay? So, and it's the angle between 0 and 180. So inverse cosine it is true. Like there's a straight up formula here. Alpha is equal to the inverse cosine of A dot B over AB. So there you go. And so I like this notation, like angle from A to B is a notation I sometimes use. Right? Now, it is not even close to obvious why there should be an equality between the products of the Cartesian components and the product of the magnitudes in that angle. That is totally non-obvious, and it would take me about a half hour to derive it. So what I'm telling you is this equality is a theorem. It's a non-trivial mathematical theorem. It is equivalent to the law of cosines. And it allows us to solve problems which are somewhat nefarious. So here's one. Actually, it's not that nefarious, but suppose you got a cube. If you've been in my Calculus 3 class, you're not allowed to participate right now. And this cube I'm going to center at the origin. All right? And my question is simply this. If we look at the origin, right, and we look at this vector here and this vector there, so say this is vector A and this is vector B, right? We'll make it a unit cube. So this point will be 0, 0, 1, and the point which B points to is going to be 1, 1, 1. Then my question is, what's this angle right here? Anybody care to guess? Yeah.
45?
45 degrees. You're the man. Thank you. I appreciate that. So we have a guess of 45 degrees. Let's see why that's wrong. So, but that is what people always guess. Yeah. Because, yeah. All right, so what is, let's see here. So we have vector A is just z hat. It's 0, 0, 1. Vector B is the 1, 1, 1 vector. All right. So A dot B is equal to 0 times 1 plus 0 times 1 plus 1 times 1, also known as 1. On the other hand, the magnitude of A is 1, and the magnitude of B is the square root of 3. All right? And I won't bother with the decimal here. All right? So then what's alpha? Alpha is equal to the inverse cosine of A dot B, which is 1, over the square root of 3. That is 57.3 degrees, roughly speaking, if I remember right. Let's see if I remembered right. Oops. Ah, man, 54.74 degrees. What's this world coming to? All right, 54.74. All right, there. As you can see, not 45 degrees. So why isn't it 45 degrees?
Like the distance between them is longer than if you're looking at 2D.
Right. So basically you're saying if you actually look at the plane and where all this stuff is happening, It's not a square, it's a rectangle, right? This is the vector that we're talking about. Excuse me. This is, in my picture, this is A, this is B, right? And so this is distance 1, whereas that distance is the square root of 3. And this distance, I think, is square root of 2, is it? I'm trying to remember. From here to here, that point is 1, 1, 0. So like this distance is square root of 2. So yeah, it's not a square. That's why it's not 45. But the thing is, there's a subset of you who are really, really good at seeing planar slices of three-dimensional geometric problems, right? And so for you, you can go a long way with your geometric intuition, right? You can go a long way, but vectors will get you much further. See, because the rest of the people here who had no idea what you're talking about, they still could calculate this angle simply by adopting the vector approach. We can always calculate the angle between vectors using this technique. We don't have to actually visualize them directly. We can just use algebra. It's an incredibly useful idea. All right, so that's the dot product. Calculating dot product is easy. There are some basic things you should remember, which is that the dot product of two vectors is a number. If you write the dot product of two vectors as a vector, you're just like daring me to take off like more points than the problem's worth. I've been thinking about negative partial credit. What about this? Like, you make an error on a problem that's so grievous to me. It's so grievous that I actually have to take points off, not just from that problem, but problems nearby. It's like, you know, what? No?
Jesus would show mercy.
Jesus would show mercy. Yes, yes. Salvation is by faith, but your grade is by works. So, let's see here. I would not cheapen grace by bringing it into academics. Let's see here. Where was I? Oh yes. Definition. A is perpendicular to B if the angle between A and B is 90 degrees. So if we think about that, if we have A dot B, right, is AB cosine of 90, well, what's cosine of 90 degrees? It is 0, right? So two vectors are perpendicular if their dot product is 0. So we can measure perpendicularity of two vectors by testing if the dot product is 0. That's nice. You can do that. We can also check for collinearity. What would it mean for two vectors to be collinear? So if this is A, right, then, well, first of all, if B is parallel, what's it look like? It would look something like this, right? Same direction, right? So in this case, you've got alpha is equal to 0. In this case, the angle between A and B is 0. In this case, A dot B is just equal to AB, because the cosine of 0 is 1. So two vectors would be parallel if their dot product is simply equal to the product of their magnitudes. Two vectors would be anti-parallel if what? Anti-parallel would mean, yeah, like this, let's say C goes this way, right? And so this time the angle between, let's say, A and C is 180 degrees. Well, in that case, A dot C would be AC cosine 180. What's the cosine of 180? It's -1, right? So that would give you A dot C is minus the product of the magnitudes. So to summarize, you can have this. Here's a little theorem for you. A dot B equal to plus or minus the product of the magnitudes implies A and B collinear. Collinear, what that means is that they lie along the same line. So collinear would include both the case of parallel and anti-parallel, which are distinguished by the angle being 0 versus being 180. Okay? So these are nice terms to use to set up problems, right? Okay. Now, there's another use for the unit vector, which is, I would say, far from obvious. That's not. No, you know, I take it back. It's actually pretty obvious. It's not. That's not that. If I can convince you with the following analogy, perhaps you'll believe me. So suppose I have the vector b. So let's see here. We're on example. Oh man, I need my glasses. Example 6. And suppose we've got the vector b is something like, oh, I don't know, 3, 1, 10. All right? 3, 1, 10. And I want to get the part of that vector that goes in the x direction. So check this out. If I do b dot x hat, in other words, I do b dot, so that's 3, 1, 10, dotted with 1, 0, 0. What do I get? Well, I get 3. Because 1 times 0 is 0, and 10 times 0 is 0. So when I take the dot product, I just get 3. So in other words, the dot product of a vector, b in this case, with a unit vector tells me the direction, tells me the length of the vector, the length of the part of the vector which lies in the direction of x. If I could draw a picture like this, you know, this is b abstractly speaking, and if this is the x direction, right, then this right here is 3, all right? So the length of the part of b which lies in the x direction is given by the dot product of b with x hat. What if I ask the same question, except instead of for x hat, I could go back to example 4, and I ask, what is the length of the part of b which lies in the direction of a? So in other words, I ask for, this is called the component of, in the a direction of b. So all you do is you take b and you take the dot product with a hat. And that will tell you the length of the part of b which is in the direction of a. If I was to draw a picture, if this is b and this is a, there's a part of a, this part right here, which we could call the projection in the a direction of b. And that will be given simply by b dot a hat times a hat. Just like 3x hat is the vector component of b in the x hat direction. So specifically here, the component in the a hat direction would be 3, 1, 10, dot product with that ever so ugly vector I had over there, which, so here's where decimals will let you down. Let's undo all this mess. Let's go back to division by root 14 to make things easier. And my vector was what? Was my, it was what, 1, 2, 3, wasn't it? 1, 2, 3. So we've got 3 times 1 plus 1 times 2 plus 10 times 3, all divided by the square root of 14. So like the length of the shadow of the vector in the direction of the other vector is, let's see here, (35) divided by the square root of 14, which works out to 9.354. And so here, this would literally be 9.354 a hat. And if you wanted to, you could put back in the details from example 4 and work out the Cartesian form of this specific vector, right? What if I asked you this question without vectors? I say you've got 2 lines in 3 dimensions, right? One of them is a finite line segment. I say, how much of this line segment, if you project it directly down onto the other line, how long is it from where the lines join? Could you answer that without vectors? I think there's some of you who could. those of you who have played sufficiently much Minecraft, and you have inculcated your mind with all kinds of three-dimensional geometry, some of us have a 3D engine built into our mind, some of us don't. But with vectors, we can answer these kinds of questions systematically. Anyway, I started a minute late, so I went a minute over. You're welcome.